When you first start working with electromagnetics, the math can feel disorienting. You are asked to navigate 3D space, tracking fields and forces across multiple axes at the exact same time. Many students hit a wall early on because they calculate distances backwards, or they mix up static coordinate points with active vectors. The good news is, mastering the strict mathematical difference between a coordinate point and a vector is a simple, repeatable process that will keep your numbers on track and save you on exams. First, we define absolute location using a position vector. It is anchored to the origin point, 0, 0, 0, and extends directly to point P. To move from point P to point Q, you need a distance vector, the relative displacement connecting them. To calculate that exact path between any two objects, we rely on the rules of vector addition and subtraction. In Part A, find the sum of two vectors using the parallelogram rule. Vectors A and B form adjacent sides. Their sum C cuts the diagonal. Part B shows the head-to-tail rule. Slide B to A's tip. The path gives the same vector C. Subtraction follows the exact same logic. If we want to subtract vector B from A, we just reverse the direction of B to create negative B, and then add them head to tail. These graphical rules prove the geometry of a path. However, to solve engineering problems, we put the pictures away and calculate the specific numerical components. The absolute rule for vector math is isolation. You must execute your operations component by component, x with x, y with y, and z with z. Here we have an origin point O with two position vectors, rp and rq, mapped out to their respective points. To find the distance vector between them, rpq, we subtract the source vector from the destination vector. Let's put this into practice using coordinates from the textbook's exercise 1.2. Our source will be point Q at 2, 4, 6. Our destination is point R at 0, 3, 8. Step 1 is converting point Q into its standard position vector format using unit vectors. This gives us 2ax plus 4ay plus 6az. Step 2, we do the same for point R. Since the x-coordinate is 0, the position vector simplifies to 3ay plus 8az. Step 3, subtract the components. X-axis, 0 minus 2 is negative 2ax. Y, 3 minus 4 is negative 1ay. Z, 8 minus 6 is 2az. The resulting vector is negative 2ax minus ay plus 2az. To find the total physical distance of that route, we calculate the magnitude. We square each component, add them together to get 9, and take the square root, giving us a physical distance of exactly 3. If you strictly follow the rule of destination minus source, grouping component by component, you eliminate directional calculation errors entirely. Now that we have the math down, let's look at a trap that catches many students during exams. A simple point is entirely static. It exists at a single coordinate and does not exert influence. A vector field is dynamic. Its magnitude and direction actively change depending on where you evaluate it in space. Treating a static location as a directional force will break your equations. Keep points and vectors completely separate in your notation. To recap, always isolate your x, y, and z axes before running your calculations. Position vectors map absolute location from the origin. Distance vectors map a relative route by subtracting the source from the destination. Getting this basic 3D grammar right prepares you for the heavier math we tackle in the next chapter, calculating the dot and cross products.